class, I want to cover 5.1, which is over area and distances. How do you find the area under a curve? So for the rest of the semester, we're going to be talking about the area under a curve. This is going to lead into integration, which is actually the opposite of differentiation. And we've already talked about antiderivatives. So we're going to tie these two things together in the next section. Let's say our function is f of x equal 1/2 x minus 2 squared, and we want to find the area under the curve from x equals 0 to x equal 2. Now, we're going to find out how to approximate the area. Remember when we first started differentiation, we really just approximated the slope of the tangent line before we actually learned the calculus that we needed to use to find the derivative, which is the slope of the tangent line. We're doing the same kind of thing here. We're going to approximate this area under the curve, and we're going to draw in approximating rectangles of equal width. The width is called delta x. The height of each rectangle is the function evaluated at the left side of the rectangle. So we're talking about the area under this curve, and we're using these rectangles. The rectangles, the height is going to be the function value, and the width is this common width called delta x. Now, we see if we just have, n equals 6 rectangles, 6, that's not going to be a real great approximation. But the idea is that if we have more and more rectangles, the area or the area that we're using, the area of the rectangles to approximate the area under the curve, it gets closer and closer to the actual area under the curve. Well, what is this idea of letting n go to infinity? That's a limit, isn't it? So we're going to find out that the actual area under the curve is defined by a limit, just like we found out that the slope of the tangent line was defined by a limit. So this is just a page where I've drawn some things in. We're looking for this area. This is the function. So the height of each rectangle, like this is f of 0, that would be the height of this rectangle. This is f of, and so our delta x in this case, I need to figure out what it is. It's always b minus a over n. So our interval was from 0 to 2. So 2 is my b and 0 is my a, and n was given and it was 6. So my delta x is 1/3. So this is f of 1/3. I add 1/3 to x each time. The width down here is 1/3, and so each time the height is the function evaluated at the next x, and we're adding 1/3 each time until we get to 5/3. Now, area of a rectangle is length times width, and so that's what we're going to use to approximate. Here again, if n goes to infinity, this is going to be the actual area. So that's the idea here. Now let's look at this example. And so in this example, I think that may be the same function from 0 to 2, but we're using 4 approximating rectangles and left endpoints. And then we want to know if our estimate is an underestimate or an overestimate. So in this case, my n is equal to 4. So one of the first things I need to do is figure out what my delta x is. That's the width of each rectangle. So delta x, the formula is always b minus a over n. So it's 2 minus 0 over 4, or it's 1/2. Now the area of the rectangle is length times width. Now it said, and this is important, it said to use left endpoints. So that means if you think about each subinterval, like this one goes from 0 to 1/2, because I'm adding delta x each time. This one goes to 1/2 to 1, from 1 to 1.5, and from 1.5 to 2. Now the height, I'm going to use the left endpoint, or the left endpoint of the subinterval. If I use the right endpoint, which I'll do in a minute to show you the difference, this first rectangle would only be that tall. Because see, I can either use the left endpoint or the right endpoint to determine the height of this rectangle. I'm using the left endpoint. So this rectangle's height is f of 0. This rectangle's height is f of 0.5. This rectangle's height is f of 1. And this rectangle's height is f of 1.5. So I can determine the area of each rectangle and add that together to get my approximation. Now, I like to write out what the subintervals are. So the first one is going, like I said before, 0 to 0.5, and I write out my 4 subintervals. Now, I'm using the left endpoints, so I'm using these values for my x. So my x0 is 0, my x1 is 0.5, my x2 is 1, and my x3 is 1.5. So I'm not going to use 2 in this calculation as an x. I'm not going to use 2 as an x value. Now the formula will be, delta x times f of x0. That's just the area of the first rectangle, and on until we get to the last rectangle. And this says area L, that means using left endpoints. And then I just factored the delta x out. Delta x is 1/2. The function was 1/2 times x minus 2 squared, I believe. Yeah. And so I'm just putting these x values into the function. So I put the 0, the 0.5, the 1, and the 1.5, and I just factored out the delta x. And then I get a number for that. I get that the left endpoints are approximately, the area with the left endpoints is approximately 1.875. Now, it's an overestimate. How do I know that? Well, if you look at what I added together, I added the area of these 4 rectangles, and that's more than the area under the curve because it goes, the rectangles go over that curve. So it's an overestimate. I know that in this particular function. Now, what I'm going to do differently in this example, well, it's actually a different function and a different interval. And I'm going to do it 4 ways, I believe, or 2 ways anyways. I'm going to use right endpoints and I'm going to use left endpoints. So you'll see what the difference is. So first of all, this is the function f of x equal the square root of x. And my delta x, you should always figure out what delta x is going to be. So delta x, where did I figure that out? Delta x is going to be 4 minus 0 over 4. So delta x is actually 1 in this case. For some reason, I didn't seem to write that in, and I'm not sure. Oh, there it is. Okay. So this is, okay, so I did leave some stuff out. So, hold on just a minute. Let me fix this page real quick, and I'll come right back. Okay, I'm back, and I think I've got it fixed now. So this is the graph of f of x equals square root of x, and my interval is from 0 to 4. N was given as 4, and so my delta x is 1. The subintervals, I'm starting at 0, and I'm adding 1 as my increment each time. These are the subintervals. Now, the first thing I'm going to do is use right endpoints. So I'm going to use the endpoints on the right of each subinterval. And then the height of the rectangle, the first rectangle, will be the function evaluated at 1, not at the left endpoint, which would actually be 0 over here. So that's what the right and left means. When I look at the rectangle, or when I look at the interval, I could either use the height to be the function evaluated at the left endpoint or the right endpoint. This, I'm using the right endpoint. So that's the height of this rectangle. The height of this rectangle is going to be f of 2. The height of this rectangle will be f of 3. The height of this rectangle will be f of 4. And so these are my x's. I'm using the 1, the 2, the 3, and the 4. Now the function is square root of x, and delta x is 1. So I just go delta x, and I put each of the x's into my function. So I put square root of 1, square root of 2, square root of 3, square root of 4. And I get this value for an estimate for the area. Now it is an overestimate because I see that this area that I'm adding in is more than the area that's under the curve. Okay, I'm going to do the same thing now, but I'm going to use, I just did it using right endpoints. I'm going to use left endpoints now. I have the same delta x, which is 1, same function, same subintervals, but now I'm using the left endpoints. So I'm using 0, 1, 2, and 3 as my x values. So the height of each rectangle is determined by the function evaluated at the left endpoint. So you notice that the height of this first rectangle is 0. So there really is no area for that first rectangle because it has a height of 0. It's really just no rectangle is there. And then the height of this rectangle is f of 1. The height of this rectangle is f of 2. And the height of this rectangle is f of 3. So the area using left endpoints is delta x, and I'm going to sum up the function evaluated at the different x's. And I get 4.1463, or approximately that. Now this is an underestimate because if you look at at if you look at the area that we're calculating here, it's less than the actual area under the curve. So this is an underestimate. So we know that the actual area is between what we got here and what we got a minute ago, which the value using the right endpoints a minute ago was an overestimate. So then the next thing we're going to do is we're going to use midpoint. Okay, so same function, same delta x, but this time we're going to use midpoints. So using midpoints, I've still got the same subintervals, but I need to determine the midpoint in each subinterval. So the first midpoint, I'd go 0 plus 1 divided by 2 is 1/2. That is going to be my first x value. And then you can find the midpoint in each subinterval, or you could just add 1 each time because delta x is 1. So 1/2 plus 2/2 is 3/2. 3/2 plus 2/2 is 5/2, and on and on. So if you think about what we're doing, we're using the midpoint of the subinterval and evaluating the function at that midpoint to get the height of each rectangle. Now, this is going to give us the best estimate, and we notice that like there's a little bit that's over here, but then it's missing some right here. So this is not going to give us the actual value because n isn't big enough, but it's going to be closer. So I've got delta x times the function evaluated at the different x values, and I get 5.388, which is the best estimate. Now, in this function, we could have, well, we don't know how to do it yet. We'll see that when we know how to integrate, we'll see how close that is, but we don't know that yet. Okay, so the definition, the area A of the region S that lies under the graph of the continuous function f is the limit, so here we go with the limit, of the sum of the areas of approximating rectangles. So this sum that is the height of the rectangle times delta x, we are now going to take the limit as n goes to infinity, and that's the actual area. And it really doesn't matter if you're using right endpoints, or you're using left endpoints, or you're using midpoints, or you're using any sample point in the subinterval. So it will all give you the actual area under the curve. Now, instead of writing out the sum this way, we use the Greek letter sigma to simplify this, and this is called sigma notation. So we use sigma, and it says 1 to n. That would be the same thing as summing f of xi times delta x from I going to 1 to n. So instead of writing this side out, we write it in this shorter notation. And so that means that the limit as n goes to infinity of this sum, that would be the actual area. And so, for example, say the function is the natural log of x over x, and the interval is from 5 to 19. We just want to find an expression for the area under the curve written as a limit. So my delta x is going to be 19 minus 5 over n. So in this case, n is going to stay n because we're trying to write out the actual exact area using the limit, my delta x is going to be b minus a over n as usual, and it ends up being 14 over n. My first x is a plus I times delta x. So a in this case was 5 and delta x was 14 over n. Then I write out the area as the limit as n goes to infinity of the sum I equal 1 to n of the natural log, because the function was natural log of x over x, natural log of this expression for my x, and then it's divided by x, and then we go times delta x. This is called the Riemann sum. This is how you would write this out as a limit. Okay? Okay. This is called the distance problem. And remember that distance is equal to velocity times time. So remember that a rate times time would give you distance. And in this case, we've got a velocity curve that is given. This axis right here represents the velocities. This axis down here represents time. And so we've got the velocity readings at different times in our time interval from 0 to 30. Now, if you think about like when we're getting the area of the rectangle, we're going height times width, but that's really going the velocity reading times the delta t. But if you go, if you actually do velocity times time, that's going to give you the distance. So the area under the curve of a velocity function is actually the distance traveled as long as the velocity is positive. So the area under a velocity curve, if the velocity is positive, from t equal a to t equal b, is the total distance traveled. Delta t in this case would be 30 minus 0 divided by 6. 1, 2, 3, 4, 5, 6. We've got 6 subintervals, and that gives me 5. So the distance I could calculate by going delta t times v of 0 plus v of 5, and I could approximate and read those off. I didn't actually do it. And that's if we're using left endpoints. And that's this picture is shown using left endpoints. So I'm going to use that idea that the area under a velocity curve is the total distance traveled. Now, if it's moving in the positive direction, if some of the velocities are negative, then the area would really be the displacement. So we'll have to be a little bit careful about that. Now, here's an example. So we've got speedometer readings for a motorcycle at 12-second intervals are given in the table. We want to estimate the distance traveled by the motorcycle during this time period using the velocities at the beginning of the time interval. So that's like the left endpoints. And then also using the velocities at the end of the time period, and that's using right endpoints. And we won't worry about C in this case. Now, so I'm really doing left endpoints and right endpoints. So here's my table. So here's my time in this row, and these are my velocities. Now, delta t is going to be 60 minus 0 divided by 5. Now, 5, be careful, there are 6 readings here, but if you think about the subintervals or the number of rectangles, it would be 5. So 60 minus 0 divided by 5 is 12. So my time intervals, and you see 1, 2, 3, 4, 5, I've got 5 time intervals. That's what n represents, is the number of time intervals. Would go from 0 to 12, from 12 to 24, from 24 to 36, from 36 to 48, and 48 to 60. We can also see that delta t is 12 because that's what you're adding to each time. That's the increment, basically. So in the A, it said that we wanted to use the left endpoints. So the readings at the beginning of the time interval. So I'm really using the left values for my x values. So my delta t is 12, and then I'm going to read off from the table the function velocity at 0 is 30, the velocity at 12 is 28, the velocity at 24 is 25, the velocity at 36 is 22, the velocity at 48 is 24, and we won't use the 60 in this estimate. We'll use it when we're using right endpoints. So I get 1,548 feet, and that's going to be an upper estimate. I kind of know that it's going to be an upper estimate because the function is, for the most part, it is decreasing. But don't worry about that right now. The B part, the only thing different is I'm going to use the right endpoints or the readings at the end of the time interval. So my readings, instead of V of 0, I'm going to start with V of 12. V of 12, then 24, 36, 48, and 60. And so I got these values off of the table, the 28, the 25, the 22, the 24, and the 27. And I get this number. So the actual distance would be somewhere in between those two values. So remember, in this section, we're really just getting approximations for the area under the curve. Well, that concludes this section, and now you can do your 5.1 homework and be sure to ask any questions.